So we've talked about pure substances and how those are broken into elements and compounds. Elements can be either atomic or molecular. Compounds can be either molecular or ionic, and so we're going to look at those differences. Most elements exist with single atoms as their basic unit. But there are 7 diatomic elements and 2 or 3, depending on who you talk to, polyatomic ions. Polyatomic elements. These molecular elements exist as molecules. So here we have chlorine gas. It is not composed of individual chlorine atoms floating around in there. They form diatomic molecules. And in a later chapter, we'll understand why they do that. They're more stable. So there are 7 diatomic elements, and we need to remember which these are, because whenever you have that element by itself, not in a compound, but by itself, it will always form diatomic molecules. So I like to personify atoms and elements and things because it makes more sense to me. I'm a visual person and I need to see what's going on, and it's a bit challenging when these things are way too small to see. So I make pictures in my mind, and I call this place Mrs. K's Chemistry Land. It's a happy place for me, but it might not be as happy for you. So in chemistry land, I think of these 7 diatomic elements as being a lot like junior high girls. I was a junior high girl at one time, and we had an assembly, and the speaker pointed out that junior high girls never go to the restroom by themselves. They always take a friend. And I was a junior high girl, and so I observed, and I'm like, oh my goodness, we do that.
Do that as adults too?
Well, we still do that as adults, but not as much, right? Yeah, if you're out with a group at a restaurant and you're going to go to the restroom, you usually take a friend with you. Guys, you might not really understand that, but the women do. It happens. So I think of these elements as being like junior high girls. And so if they are alone, not with some other elements, they're going to use the buddy system, and they're going to go around holding hands. Okay, so there's 2 of them together. There are scientific reasons behind that, but those are harder to remember. Phosphorus and sulfur also make molecules, but their molecules have more than 2 atoms, so they're called polyatomic elements. And I want you to be aware that phosphorus and sulfur do that, but that's never going to come up on an exam. Polyatomic elements, yeah. So here's a periodic table showing which of these are molecular elements. And so here in the pink, phosphorus, sulfur, and selenium. Those are the elements that form polyatomic molecules. Just be aware that they can do that, but I won't test you on that. The yellow ones are the ones you need to know. And there's a couple of different ways that you can remember these. I think it's pretty cool. There's 7 of them, and if you start with element number 7 and you make a 7 on the periodic table, that's most of them. And then hydrogen's over here because it just has to be an exception to everything. And we'll see that over and over. Everybody does this, and hydrogen does something else. Okay, so that's one way to think about it. Another way is a mnemonic or a silly sentence. So, horses need oats for clear brown eyes. For clear, there's the chlorine. Brown, oops, that's a bad B. Brown, Br for bromine. This gets a little sketchy here. Eyes. Sometimes you got to just stretch it a little bit. Horses need oats for clear brown eyes. Hydrogen, horses need nitrogen, oats for clear brown eyes. Okay, so that's a good one.
That's a good mnemonic.
Yeah, I like it. Somebody told me one last fall, and it was, have no fear of ice cold beer. So, if you like that one better, I don't think that one fits as well, because it doesn't, this one has Cl for chlorine and Br for bromine, and the other one doesn't. The one I remember from high school was Brinkelhoff. Brinklhof. And that's someone's attempt to make a pronounceable word out of the element symbols, Brinkelhoff. So whatever you choose as your method for remembering this, you need to know these. Because whenever we have these seven, any of these 7 elements by themselves, not in a compound. So chlorine, when she makes a compound with sodium, that's like her boyfriend. She doesn't need her girlfriend with her anymore because she's with the guy. They just don't like to be by themselves. They don't like to be individual atoms alone. So they're going to either be with another element or with their sister friend. Okay? Any questions? Some of my stuff gets even sillier than that, just to warn you. Okay, so those were the molecular elements. Molecular compounds have 2 or more elements that are covalently bonded together. They are going to be nonmetals. So the basic unit here is a molecule. We have the examples of water. Water is composed of H2O molecules. Dry ice is composed of CO2 molecules. Propane, which is what you have in that cylinder maybe on your back patio for the grill, is C3H8. And so if you were able to zoom in and look at those, these are space-filling models of propane molecules. Okay, and so they are individual molecules that are together in that canister. Any questions? It's different than ionic compounds. Ionic compounds, there's a transfer of electrons. Then you have a positive electron, a positive ion, and a negative ion, and they're attracted to each other. Here, there's no positives and negatives in terms of ions. They're sharing electrons. Ionic compounds, we've got the metal and the nonmetal. The metals form the cations. I think of the metals as being masculine and the nonmetals as being non-masculine, feminine, right? So cations and anions. So the ionic compound, you've got cations and anions together. There is no molecule in an ionic compound because a molecule is a discrete unit. It's separate onto itself. In these salt crystals, we just have an extended alternating arrangement of cations and anions. So you could say that each of these is its own molecule because it's the unit, but each of those units is going to have a different number of ions in it. The ratio will be the same. It's always 1-to-1. But each individual piece of sodium chloride is going to have its own number. And because they're all different, it's not useful at all to think of it that way. So for ionic compounds, we think about a formula unit. The formula unit is just the smallest electrically neutral collection of ions. It is the empirical formula for that substance. So sodium chloride, depending on the size of the piece, just lots and lots of sodium and chloride ions. But the ratio is always 1-to-1. And so we give the formula as NaCl because we have sodium ions and chloride ions in a 1-to-1 ratio.
So the formula unit is the empirical formula?
Yes. Yeah, it's basically the empirical formula. It's the lowest ratio. We can also have polyatomic ions, and these should be familiar to you because I put them on that list of things to memorize. The polyatomic ions, like their name suggests, polyatomic, they have many atoms. So these are ions where we have a collection of atoms that are covalently bonded together, but it's not a molecule because it has an overall charge. And so we call those polyatomic ions. These are found in ionic compounds, and so we see things like NaNO3. So in this class, ionic compounds are always going to be composed of two different ions, one kind of cation and one kind of anion. So here we have three elements. The metal is the first ion, the cation, and everything else is the second ion, the negative ion. It's a polyatomic ion. It's NO3 minus, and it has a name, nitrate. And its name is nitrate because we decided to call it that. And it has its formula because we observed that that's the formula that it makes. So, I know some of this can be really confusing. It's not my fault. I'm trying to make the best of what is, right? So this is CaCO3, again, an ionic compound. You identify ionic compounds by looking at that first element. If the first element is a metal, it's going to be an ionic compound. So we've got the calcium ion, and then everything else, the CO3 is the anion. It's a polyatomic ion. KClO, sometimes students, want to see, oh, well, this is a potassium ion and a chloride ion and an oxide ion, right? They want to divide everything up. You can only make two pieces, the metal first, and everything else goes together. So we'll talk some more about these later. So we should be able to look at substances like this and identify, is it an atomic element, a molecular element, is it a molecular compound or an ionic compound? So just clues about identifying elements versus compounds. All elements have a single name. Most compounds have two names, just like most people go by a first name and a last name. So if you see two names, it's going to be a compound. If you see a single name, the chances are good it's an element. Okay, so let's look at this one. Fluorine. First of all, is it a compound or an element? It's an element. Okay, so I'm going to write E. Now the question is it atomic or molecular? Molecular. Horses need oats for clear brown eyes. So this is a molecular element. When we write the formula for fluorine, it's F2, because fluorine atoms don't like to be by themselves. If there's no metals for them to hang out with, they're going to share electrons and buddy up with another fluorine atom.
So diatomic elements are molecular?
Yes, because they form diatomic molecules, two atoms covalently bonded together. Okay, N2O, element or compound? Compound, right? We have two capital letters. That's a dead giveaway. This is a compound. It can't be an element. So this is a compound. And then we have to say molecular or ionic. Okay, I heard both. You guys are doing a great job of answering. By the way, I love it. I can actually hear you. What we want to do is we want to look at the first element. Is it a metal? No. This is a nonmetal and a nonmetal. So this can't be an ionic compound. It's a molecular compound. How do we know it's a nonmetal? We look on the periodic table, and there's that stair-step line. If it's to the right, it's a nonmetal. If it's to the left, it's a metal. Don't rely on your knowledge of common substances for this, because, some of them, like francium, what the heck? Is there an element francium? Yeah, there is. How would you be expected to know what it is? You wouldn't. You look it up in the periodic table. So two nonmetals, molecular compound. How about this one, silver? Element or compound? Element. Atomic or molecular? Atomic. It is not one of Brinkelhoff or Have No Fear of Ice Cold Beer. And it's not those other little guys in there, phosphorus, sulfur, or selenium. So that's an atomic element. Silver exists as individual atoms, not covalently bonded to each other. Letter D, is that an element or a compound? That's a compound. Ionic or molecular? Ionic. Because we look at that first element, potassium. We look at the periodic table, it's on the metal side. We have a metal and a nonmetal. It's an ionic compound. Metals are not good at sharing. They don't share well. The metal's going to say, no, here, you just take my electron. You can have it, right? And the nonmetals are like, oh, great, he's just giving it to me. And then after that happens, they're really attracted to each other. They stick together. And my 8-year-old would say, ick. How about this one? What is that? Ionic compound, molecular compound, atomic element, molecular element. Ionic compound. It's got 2 elements. It's a compound. The first one is iron. Iron's a metal. Metal, nonmetal, ionic compound. Everybody get that? This is the key to being able to name compounds. We first have to identify, is it ionic or molecular? Because those 2 kinds of compounds have different rules for how the compounds are named. And this is much like how people name their children in different cultures. My ancestors came from Sweden, and they don't do this anymore, but they used to give the father's first name as the child's last name. And if you were a boy, it would be your dad's name with son afterwards. So if your dad was John, your last name would be Johnson, if you were a guy. If you were a girl, your last name would be Johnsdotter. You can imagine that, I mean, there's some beauty in that system, but then it gets a bit confusing too, because everybody's last names are different and they keep changing generation to generation. There are other cultures where everybody has basically the same first name, and it's the last name that identifies who you are. And then some cultures, you just use a single name, right? So you have to understand which culture these compounds are from, so that you can apply the rules correctly. Okay? So classifying substances.